Hi everyone! In this video we're going to talk about the Oxymercuration Demercuration reaction. It allows us to make alcohols from alkenes, but without rearrangement. Earlier we learned about the acid-catalyzed hydration of alkenes. It proceeds through a carbocation intermediate, and depending on what kind of alkene you're starting with, the carbocation could rearrange to a more stable carbocation. Then the subsequent alcohol that would form would have the OH group in the position of the rearranged carbocation. The oxymercuration demercuration reaction, however, allows us to form the Markovnikov alcohol product, but bypass any rearrangement. So let's take a look at the ingredients of this reaction and the mechanism so that we can understand how that happens. The oxymercuration demercuration reaction converts alkenes into alcohols with the Markovnikov regiochemistry. This reaction takes place in two steps, and to carry out the first step, which is the oxymercuration, we're going to need mercury acetate dissolved in THF and water. Then for the second step, which is the demercuration step, we're going to need sodium borohydride and an aqueous base. And again, the purpose of using all these complicated reagents is to avoid rearrangement. The nucleophile in this reaction is the alkene, and the electrophile is the positively charged mercury atom. Now let's take a look at the mechanism of this reaction so that we could understand how the rearrangement is avoided and how mercury acts as the electrophile. The mechanism of this reaction begins by dissociation of mercuric acetate into an acetate ligand and a positively charged mercury acetate complex. In the second step, the electrons from the alkene attack the positively charged mercury atom, resulting in a three-membered mercuronium ion. In this ion, the positive charge is distributed between the mercury and one of the carbons. The key to understanding this reaction is recognizing that there's sort of a carbocation structure, but it's not a full formal carbocation, but rather the charge is distributed. Nonetheless, because there's still a partial positive charge sitting on one of the carbons, it's going to prefer to sit on a carbon that is more substituted. In this case, the secondary carbon as opposed to the primary carbon. Another thing to know is that the partial positive charge sitting on that carbon is locked into place by the three-membered ring. And because of this, and because of only the partial nature of the carbocation, the rearrangement cannot take place. The partial positive charge on the carbon nonetheless makes it a great place for a water molecule to attack. And so the third step of this reaction involves a water molecule attacking the partially positive carbon of our substrate. This results in the ring opening with the electrons moving fully over onto the mercury, resulting in the following intermediate structure. The protons on the oxygen in our intermediate structure are actually quite acidic. So in the fourth step, the solvent water molecule can remove one of these protons, giving the electrons to the oxygen. And this results in an alcohol. However, notice that the mercury acetate is still attached to this compound. So in order for us to make our desired alcohol product, we have to remove this, and we do so with the second step, the demercuration step, for which we're going to use sodium borohydride and aqueous hydroxide. In the second step, we're going to need a hydrogen atom to replace the mercury acetate. So we use the sodium borohydride, and the hydride attacks the carbon and kicks out the mercury. And there's also aqueous hydroxide in this reaction, so after a couple of mechanistic steps, we get our final alcohol product and some of the byproducts. So this is how we get Markovnikov alcohols from alkenes, but without the rearrangement. Now let's compare what happens to an alkene when it's exposed to these two different conditions. On top we have our acid-catalyzed hydration conditions, and on the bottom we have the oxymercuration demercuration conditions. When this alkene is exposed to the top conditions, then one of the methyl groups will move over in order to accommodate the more stable carbocation, and so the hydroxide will add to the carbon that formerly contained one of those methyl groups. However, in the second set of conditions, that methyl group does not move over, and we get the hydroxide added to one of the alkene carbons in the Markovnikov regiochemistry. Hope the mechanism of this reaction was easy for you to follow. Good luck studying, and I will see you soon.